Hello. In today's lecture, we're going to be going through some of the questions from tutorial 4 on first-order differential equations. Okay, so this tutorial covers some of the methods that we discussed in class. Okay, so let's look at the first part on direct integration. So 1.1, we have dy by dt is equal to t cos t. Yeah. And we know that we can just directly integrate because the right-hand side has no y dependence. So we can integrate the left-hand side to get y, and we can just integrate the right-hand side. Yeah, but since it's a product of two functions, we're going to have to use integration by parts. So we end up with t sine t minus the integral of sine t dt. And that gives us y is equal to t sine t plus cos t plus c. Yeah, where c is some constant. And if we're given some initial condition, we can then solve for c. For example, if y at 0 is 1, for example, then we can substitute this in and solve for c. So we can have 1 is equal to, t is going to be 0. So we're going to have 0 sine of 0 plus cos of 0 plus c. The first term vanishes, the second term is 1, so c is going to be 0. Okay, so given this initial condition, we have y is equal to t sine t plus cos t plus 0. Yeah, and then of course that will change if we change the initial condition. Yeah, let's look at the next one, 1.2. We have dy by dt is equal to t e to the minus t squared. Yeah, again, the right-hand side doesn't depend on y, so we can directly integrate. So y is equal to the integral t e to the minus t squared dt. Yeah, now if we look in the exponent there, we have minus t squared. If we imagine doing a u substitution, differentiating that will give us minus 2t. However, we've got a t in front. So it's almost what we would need for a u substitution. But what we can do is manipulate this slightly so that we don't actually need to do a u substitution. So what I mean by that is we need minus 2t dt as our du part if we were to do a u substitution. So let's multiply and divide by minus 2. So we're going to have minus 1/2 integral e to the minus t squared, and then minus 2t dt. Yeah, I'm just grouping that together to show what we would have if we did a u substitution. But now notice that this takes the form of e to the u du, okay, which if you do a u substitution, that becomes very easy to solve. So this just becomes y is equal to minus 1/2 e to the minus t squared plus c. Yeah, so there's no need to do that extra work of letting u be minus t squared, finding the derivative, substituting. We can just do it right away because we know that if we were to do a u substitution, it would just become e to the u. Yeah, so it just takes fewer steps to do. Okay, and again, we can solve for c using some initial condition. Okay, so most of the time that will be provided. If there is no initial condition provided, then we just leave it as plus c because that's undetermined. Okay, so 1.3, we have dy by dt is equal to t natural log of t. And again, we can just directly integrate. So y is equal to the integral t log t dt. Okay, and again, since we have a product of two functions, like we had before, over here with t cos t, we can do integration by parts. So we let u be the natural log of t, because when we differentiate that, we get 1 over t, which will cancel nicely with the t squared that we get from integrating our dv. Okay, so just on the side, we can have u as the natural log of t, dv is equal to t dt. That makes things a lot easier, because integrating the natural log of t is quite difficult, so we would rather differentiate that. Okay, so this is going to give us 1/2 t squared, the natural log of t, minus the integral of 1/2 t squared times 1 over t from differentiating the natural log dt. So y is going to be 1/2 t squared, natural log of t, minus will be 1/4 t squared plus c. Okay, and again, we can determine c if an initial condition is provided. If it's not provided, then we just leave it like that. Okay, lastly, 1.4. We have dy by dt is equal to t squared natural log of t squared. Okay. Now this looks like what we had before, but it's a bit more complicated because of the t squared. However, note that in the natural log, if we have something to an exponent, this exponent can be taken out. So the natural log of t squared is 2 times the natural log of t. And then that simplifies this a bit. So dy by dt, dy by dt is going to be 2 times t squared, the natural log of t. Yeah, so we can do the same thing as before. We let u be the natural log of t to differentiate. We let dv be 2t squared to integrate. So y is going to be the integral 2t squared, natural log of t dt. So y is equal to, we're going to have 2 over 3t cubed from our v term times the natural log of t minus the integral 2 times the integral 1/3 t cubed from our v term times 1 over t from our du term dt. So y is equal to 2/3 t cubed, natural log of t, and then the t cubed over t, that will make it t squared. So that gives us another 3 in the denominator. So it will be minus 2 over 9 t cubed, and then plus c. Again, we leave that to be determined later when we're given an initial condition. Okay, so this was the direct integration method, where the right-hand side only depends on t. So we can just integrate the left-hand side, integrate the right-hand side, and get our solution. And if we're given an initial condition, we can then solve for c. Okay, let's have a look at part 2. Okay, with different integration methods, the separation of variables, and homogeneous and linear and so on. Okay, so 2.1, we have dy by dx is equal to x squared over y squared. Okay, now this can be done 2 different ways. We can either use separation of variables, where we take the y terms over to one side. So we have y squared dy is equal to x squared dx. Integrate both sides and we get our solution that way. Or we can use the work we did on homogeneous equations. Remember, we said u is equal to y over x. And then we changed everything to be in terms of u. So we let y over x be u. We find y prime in terms of u. and then solve the equation in terms of u, and then go back and replace this with y is equal to u times x. So we've just solved for u, we times it by x, and that gives us back our solution in terms, our solution with y. Okay, so maybe you can try that for homework. So solve this using this homogeneous way. Okay, but let's do the separation of variables. This is going to be 1/3 y cubed is equal to 1/3 x cubed plus c. Okay, now just to simplify things, we can multiply through by 3. So we get y cubed is equal to x cubed plus c1, where c1 is a different constant because we multiplied c by 3. So c1 is 3 times c, but again, that's just a constant. Okay, now we can take the cube roots on both sides. So we get y is equal to x cubed plus c1 to the 1/3. Yeah, and c1 will depend on some initial condition provided. Yeah, let's look at 2.2. So we have dy by dx is equal to 6x squared over 2y plus cos y. Yeah, again, we see this distinction between the x terms and the y terms. So everything at the bottom, that just depends on y. So we can take that over to the other side. So we have 2y plus cos y dy. We can take the dx over and we get 6x squared dx. Okay, so we have successfully separated the variables. So let's integrate. So integrate and integrate. Here we're going to get y squared plus sine y is equal to 3x cubed. 2x cubed plus our constant c. But now notice that this left-hand side, the y squared plus sine y, that is not an invertible function. So we can't directly solve for y. Okay, so we end up with an implicit equation. Okay, so we don't have y explicitly dependent on x, but we know that this is actually a function of x. So we have y of x squared plus sine y of x is equal to 2x cubed plus c. Okay, so we have our implicit equation here. Okay, 2.3. We have dy by dx is equal to x squared y. And again, we've got that separation of variables. We've got the x terms and the y terms being multiplied together, and we can take the y term over to the other side. So we're going to have 1 over y dy is equal to x squared dx. There we can integrate both sides. Integrating 1 over y, that becomes the natural log of y. Integrating x squared, that's going to become 1/3 x cubed, and don't forget the plus c. Now, we don't want the natural log of y, we want y, so we can exponentiate both sides. So y is equal to e to the 1/3 x cubed plus c. But this we can write as e to the 1/3 x cubed times e to the c. But e to the c is just another constant because c is a constant. So we can write this as a e to the 1/3 x cubed. And that's pretty much the standard that we use. Okay, so whenever you have the exponential of something plus a constant, we can always take that out as a multiplicative constant in the front. Yeah, so you'll see that's kind of the standard way of writing the solutions. Okay, 2.4, the last one for separation of variables. We have dy by dx plus x e to the y is equal to 0. Okay, now this doesn't look like the standard separation of variables, but notice that the x terms and the y terms are just multiplied together. So this is separation of variables. We just need to take that over to the other side. So we have dy by dx is equal to minus x e to the y. Now we can do our separation. So the e to the y we can take over to the other side. So we have e to the minus y dy is minus x dx. Then we can integrate both sides, and we get minus e to the minus y is equal to minus 1/2 x squared. And then I'm going to write minus c. Okay, now, of course, you could have written plus c, but it's constant, so it doesn't matter if you put a plus c or minus c. The exact value is determined later on. But the reason I put the minus c is because now we can multiply through by minus 1, and we get e to the minus y is 1/2 x squared plus c. Okay, of course, it doesn't make much of a difference, but now we've got everything being positive. I guess it just looks a bit better. Okay, now we can take the natural log on both sides. So we get minus y is equal to the natural log of 1/2 x squared plus c. Then take the minus over, so we have y is equal to minus natural log of 1/2 x squared plus c. Yeah, and again, c is determined later on with some initial condition. Okay, the next part 3, is on linear equations. So remember, those are the ones where we need that integrating factor to solve. Okay, so let's look through those. 3.1, we have xy prime minus 2y is equal to x squared. Yeah, but this is not in our standard form because we want something like y prime plus p of x times y is equal to q of x. Here we've got this x in front, and we don't want it there. So let's divide through by x. So we have y prime minus 2 over xy is equal to x. Now we can find our integrating factor mu. So that's going to be e to the integral minus 2 over x dx. Okay, that will be e to the minus 2 natural log of x. But we can write that as 1 over x squared. Okay, so that is our integrating factor, which means we can rewrite this equation as y over x squared prime is equal to x over x squared. Okay, or just 1 over x. Now, the left-hand side is just a prime term, so we can integrate both sides, get rid of the prime, and then we can solve for y. So if we integrate both sides, we get y over x squared is equal to the natural log of x plus c. Okay, so where c is some constant. Now we can multiply through by x squared, and we get y is equal to x squared, the natural log of x, plus c times x squared. Yeah, and that gives us our solution. Let's have a look at the next one, 3.2. Okay, so here we have y prime is equal to y minus x. Okay, again, this is not in standard form, so let's move the terms around so that it looks like what we want. So we're going to have y prime minus y is equal to minus x. Now we have our function p of x being minus 1. So mu is going to be e to the integral minus 1 dx. So that's e to the minus x. Okay, so we've got our integrating factor. We can rewrite the equation as y times e to the minus x prime is equal to minus x times e to the minus x. And again, we can integrate both sides, to get rid of that prime there. So y e to the minus x is equal to minus integral of x e to the minus x dx. Yeah, we can integrate that out. So we get y e to the minus x is equal to x times e to the minus x minus the integral of e to the minus x. Okay, one last integral to do. We get y e to the minus x is x e to the minus x plus e to the minus x, and then plus c. Okay, now we can multiply through by e to the x. So we get y is equal to x plus 1 plus c e to the x. Yeah, and that gives us our solution. Okay, last one for linear differential equations, 3.3. We have 4x cubed y plus x to the 4 y prime is equal to sine cubed x. Okay, again, it's not in standard form, so let's rearrange the terms a bit. So we can divide through by x to the 4, and we get y prime plus 4 over x y is equal to 1 over x to the 4 sine cubed of x. Okay, that was just with a bit of rearrangement to get it into that standard form that we want. Now we can find our integrating factor, mu, so that's going to be equal to e to the integral 4 over x dx. So that's e to the 4 natural log of x, or just x to the 4. Okay, so we can rewrite the equation as y times x to the 4 prime is equal to x to the 4 over x to the 4. So that's just sine cubed. So that's sine cubed of x. Okay, now we can integrate both sides. So we have y times x to the 4 is equal to the integral sine cubed of x dx. Okay, we can factor out one of those sine terms. So we have y times x to the 4 is equal to the integral sine squared times sine x dx. Now, if we write that sine squared in terms of cos, then sine x dx would be the differential of cos. So imagine a u substitution where u equals cos, then sine x dx becomes du. So let's do that. So y times x to the 4 is equal to the integral sine squared, we can write as 1 minus cos squared. Okay, and then we have sine x dx. Okay, but the derivative of cos is minus sine, but we've got sine. So we can multiply and divide by minus 1 to make this into the better form for a u substitution. So we have y times x to the 4 is equal to minus the integral 1 minus cos squared. And then we have minus sine x dx. Okay, so that makes it much more clear that we want to be doing a u substitution. So if u is going to be cos, we already have our du, so we can just integrate that. So y times x to the 4 is equal to minus, and then this is going to give us x. Oh, sorry. Cos x minus 1/3 cos cubed x plus c. Okay, so multiplying through by x to the 4 is going to be y is equal to minus x to the 4 cos x minus 1/3 cos cubed x plus c times x to the 4. Okay. So let's take a look at the next part on exact and inexact differential equations. Exact and inexact. Okay, so 4.1, we have the differential equation 2xy minus 9x squared plus 2y plus x squared plus 1 dy dx is equal to 0. Okay, so that's not the standard form that we want. So let's multiply through by dx. So we're going to end up with 2y plus x squared plus 1 dy plus 2xy minus 9x squared dx is equal to 0. Okay, so now we want to check if this is exact or not. So the way that we do that is we imagine that this first part, the one with the dy, is df by dy. Okay, so we imagine there's some function f such that df by dy gives us this term in front of dy, and df by dx gives us this term in front of the dx. In other words, this whole thing is equal to df, our differential. Now, we know that if we have df by dy and df by dx, then the mixed derivatives will be equal. So this is exact if and only if d by dx of df by dy is equal to d by dy df by dx. So if the mixed derivatives are equal, then we call this exact. Okay, so we know the df by dy is the first part, so we take the x derivative of this y term and the y derivative of the x term, and we check if they're equal. So d by dx of this first part, 2y plus x squared plus 1. Yeah, that's going to just be 2x. And then d by dy of the other one, so we have 2xy minus 9x squared. This is going to be equal to 2x. Okay, so they're equal, which means this is exact. Yeah, since it's exact, we can now find this function f. Yeah, find the function f, and that will give us our solution of y in terms of x. Okay, so we know that this gives us something like df is equal to df by dx dx for this x term on the right there, plus df by dy dy for that y term, which is first over here, and this is equal to 0. Okay, so since it's equal to 0, we know that this f of xy must be a constant. So we're going to be using that at the end. Some constant c. Okay, but we know that the term in front of dx is going to be df by dx. So we can write df by dx is equal to 2xy minus 9x squared. Yeah, because that's that term in front of the dx. Now we can integrate through with respect to x. So we get f of xy is equal to the integral of 2xy minus 9x squared dx. But we need to add some function of y. So that's a y. We need to add a function of y because when we do the partial derivative with respect to x, that vanishes. So that's very similar to if we have some function of x and we integrate with respect to x, we need to add a constant c, because the derivative with respect to x will get rid of it. Same thing here. The derivative with respect to x will get rid of this function of y, so we need to add it back when we do the reverse. Okay, so f of xy is going to be equal to x squared y minus 3x cubed plus this undetermined function of y. Okay, so that's the first part. Now we do the same thing with the y term. So we have df by dy is equal to 2y plus x squared plus 1. Yeah, that was this y term in front. So we integrate with respect to y. So f of xy is equal to the integral 2y plus x squared plus 1 dy plus some other function, but now with respect to x. Okay, for the same reason as before. Okay, so f of xy is going to be equal to y squared plus x squared y plus y plus some function of x. Now note that we have two different functions, but it's the same thing. So the first one we found was x squared y minus 3x squared plus some function of y. Then we have the same function written as y squared plus x squared y plus y plus some function of x. But these must be equal. It's the same function. So that means g1 has to be y squared plus y, because that is has to be common between the two. So g1 of y must be y squared plus y, and g2 of x must then be minus 3x cubed. If we choose g1 and g2 to be those, then we have that these two match, yeah, which is what we want because it's the same function. Therefore, f of xy is equal to minus 3x squared plus x squared y plus y squared plus y. And this is equal to some constant c. We said that above here. Yeah, and then that will give us our solution. So if we solve for y in terms of x, that gives us our y of x. Okay, so here that is possible because it's quadratic in terms of y. So we can use the quadratic formula, but that's too much work to do. So we can just leave it like this. Okay, so let's look at the next one, 4.3. Okay, so we have following 3xy plus y squared dy plus x squared plus xy dx is equal to 0. Okay, and we want to check if this is exact or not. Okay, which means we need to take the x derivative of this first term, because that's the dy part. So d by dx of the first part, 3xy plus y squared, that's going to be 3y. Taking the y derivative of the second part, that's going to be d by dy of x squared plus xy. That's going to be x. Okay, and clearly they do not match. So this is not exact or inexact. Yeah. But we can make this exact using an integrating factor. So I'll leave that for homework to find the integrating factor. But we're given that it should be x. Okay, so we're given what it is, and we need to show that it becomes exact but it's good practice to see where that x comes from. Okay, so a little bit of homework. Show that the integrating factor is x. Okay, so 4.4. We know that mu is x, so we can multiply through by that. So we have x times 3xy plus y squared dy plus x squared plus xy dx with the x in front is equal to 0. Sorry. Yeah, equal to 0. Okay, so now we have 3x squared y plus xy squared dy plus x cubed plus x squared y dx is equal to 0. Now we can take the, sorry, I think I made a mistake here. 3xy plus y squared dy, yeah, and x squared plus xy dx, yeah. Okay, so we need to take the x derivative of the first part, so d by dx. 3x squared y plus xy squared. This is going to become 6xy. So 6xy plus xy cubed, so that will be plus y squared. Sorry, I think I made a mistake somewhere here. Okay, so it's 3xy plus y squared dy plus x squared plus y dx. Yeah, that's right. X squared y. Yeah, okay. And then d by dy of the other part, the x cubed. Sorry, I messed up with the dy and dx. Let's just fix that. So these are supposed to be the other way around. Okay, so the first one is dx, and then the second one is dy. Okay, so let's carry on now. So the first one is the one with dx, so we need to differentiate that with respect to y. So we have d by dy of 3x squared y plus xy squared. This is going to be 3x squared plus 2xy. Then the second one is the term with the dy, so we differentiate with respect to x. So we have d by dx of x cubed plus x squared y. That's going to become 3x squared plus 2xy. And we see that those are now equal, which means this is exact. Since it's exact, we can find our function f. So df by dx is going to be equal to the first part, the 3x squared y plus xy squared. Yeah, then we can integrate this. So f of xy is going to be x cubed y plus 1/2 x squared y squared plus some function of y. We don't know what it is yet. Then we have df by dy is going to be that other term, the x cubed plus x squared y. Okay, this other part here. Then that means f of xy is going to be x cubed y plus 1/2 x squared, sorry, 1/2 x squared y squared plus some function of x. Here we don't know what that is. So now comparing the two, we see that they have the same terms, So G1 and G2, they must just be some constant. Therefore, f of xy is equal to x cubed y plus 1/2 x squared, y squared, and that must be equal to some constant, c. And then again, this is quadratic in y, so we could solve for y using the quadratic formula, but that's a bit too much work for now. So we'll just leave it like that. Okay, so that is it for tutorial 4. The next lecture video to be posted will be on the second order differential equations, and that will go with tutorial 5. Okay, so next week, Wednesday, we will have part of the tutorial period being a lecture on second order differential equations, and then the remaining parts will be the normal tutorial going through the questions. Okay, as always, if you have any questions, please just send me an email. I'll be happy to help you out.